This is a video on probability. What I'm going to discuss is I'll talk about the definition of probability. I'll talk about the addition rule for probability. I'll talk about the multiplication rule for probability. And we'll also look at contingency tables and finding probabilities using these tables. And finally, I'll do a little example with the lottery. So let's start out with the definition of probability. First, we need to say what an event is. An event is any collection of outcomes of a procedure. So if the procedure is to roll a die, an event is either a 1, a 2, a 3, a 4, a 5, or a 6. Those are each events. Or possibly an event is rolling an even number. That's an event. So a simple event is an outcome that is not a collection of simpler components. So for example, rolling a die, rolling a 2 is a simple event. On the other hand, rolling an even number is not a simple event because rolling an even number is a collection of a 2, a 4, and a 6. So the sample space is the collection of all possible simple events. So for rolling a die, for example, it's a 1, 2, 3, 4, 5, and 6. For picking a card, it's all of the 52 different cards that you can pick when you pick a card. So it's all the different events that could happen. So now for the big definition. This is a definition of probability. And what it says is that the probability of an event A happening is equal to the number of simple events in A divided by the number of simple events in the sample space. So for example, the probability of rolling an even number is 3 divided by 6 because there are 3 even numbers, 2, 4, and 6, and there are 6 different die rolls that could happen. 1, 2, 3, 4, 5, and 6. So the probability of an even number is 3 divided by 6. This doesn't sound too hard, especially when I say it, but it turns out counting the simple events and keeping track of the simple events, that actually could be quite difficult. We're going to have all kinds of rules that will help us out and also might confuse you, and I'll try to be as non-confusing as possible. So now let's talk about a very important piece of probability that we're going to be using over and over again in the course on statistics. And that is called the law of large numbers. And what it states is that if an experiment involves many trials, then the proportion of successes will likely be very close to the theoretical proportion. So that's a lot of definition there. Let me kind of remind you that there's some words here that aren't very mathematical, and all of statistics, or a lot of statistics, is dealing with that and kind of turning that all into mathematics. So first thing, many trials. What does that mean? That just means that you have to have a large number of trials, and not today, but another time in statistics, we'll talk about how many is enough trials to consider it many. The other is likely to be. That also is kind of an ambiguous word right there. What does it mean to be likely? Well, we're going to find out that means the probability is very large that it will happen. Even that is strange. So large for us will often be greater than 95% or greater than 99% chance. Also very close to the theoretical proportion. That very close is another word that's not very mathematical. So we'll be talking about that throughout this whole course. So very close might mean within, say, 0.02%, or it might be within 1%. So again, there's lots of ways of talking about what very close means. The theoretical proportion, that is, if you're rolling a die, for example, rolling a 1, the theoretical proportion would be 1 out of 6. If you were looking at the college students in America, and you're looking at the probability of picking a woman, if you randomly selected a college student, then that would be the total number of women of all American college students over the total number of American college students. And that would be the theoretical proportion for that. Now, of course, you would never count all the people who are in college. Instead, you would take a sample. And what this says is that if we have a very large sample size, that's the many, many trials, then we could say that the proportion of women in the sample is very likely to be very close to the proportion of women of all American college students. So that's what the law of large numbers tells us. The main thing for us in this class is that it's going to say that if we have a very large sample, then the proportion that we're interested in for the sample is going to be very close to the proportion for the population, when the population is a very large, in the millions usually, population. And that's going to be the law of large numbers for us. More theoretically and more experimentally, here's an example here. If you toss a fair coin 1 billion times, it's highly likely that the proportion of heads will be very close to 50%. So if you tossed a coin 1 billion times, first thing, you would probably tire out of exhaustion and die before you finish tossing the coin. But let's say you simulated tossing a coin on a computer 1 billion times. Computers tend not to get tired like we do tossing a coin and really bored. But if we simulated tossing a coin 1 billion times using a computer, then we would expect to get a very close to 50% heads and 50% tails. We may not get exactly 50%, we probably won't, but we might get 49.99999% heads, and that's what the law of large numbers says. It'll be really close to 50%. So let's talk about an important rule in probability called the addition rule. So to talk about that, first I want to talk about a little bit of vocabulary, or symbolism, I guess. And that is, we always use the word P to represent the probability of, and A and B typically are the letters we're going to use to talk about events occurring. And then OR is going to mean that either A occurs, B occurs, or both occur. And that's going to be probability of A or B means one of the two or both of the two occurred. So what the addition rule says is it helps us find out what the probability of A or B is. And that is that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So A and B means both of them must have occurred for that to be true, to include that in that probability. So for example, let's suppose that a room has 4 girls, 3 women, 2 boys, and 6 men. So let's find the probability of a male or a child. So I'm going to let M correspond to being a male. So males are boys and men, of course. And children are boys and girls. So we can use the addition rule, and that says the probability of being a male or a child is equal to the probability of being a male plus the probability of being a child minus the probability of being a male and a child. And let's look at the numbers for that. If you look at the males, well, there were 2 boys and 6 men. That's 8 total males in the room. Out of 15 people in the room, that was 4 plus 3 is 7, plus 2 is 9, plus 6 is 15. That's where I get the denominator. And then plus the probability of being a child, well, there are 4 girls and 2 boys, so there are 6 children. So that's where I get 6 divided by 15 total people in the room. And then to be a male child, that means the person is a boy. And there are 2 boys in the room. So the probability of being a male and a child is 2 divided by 15. And notice that 8 over 15 plus 6 over 15 minus 2 over 15 is equal to 12 over 15. And you could put that in decimal form. You could reduce the fraction. I'm not that interested in that. More, I want you to understand how to use the addition rule to calculate probability. So now I'm going to talk about the rule of complements. So first let's talk about some symbols that are used for complements. Sometimes they'll use an A prime. Sometimes you'll see an A with a C as a superscript. Sometimes you'll see an A with a bar on top. There's lots of different symbols. Here I just write A prime. And we call that the complement of A. And what that means is it represents the outcome of A not occurring. And the big rule says that the probability of A not occurring is equal to 1 minus the probability of A occurring. This will make total sense as soon as you see an example. So the example I have is that if the probability of winning the game is 0.2, so 20%, then the probability of losing is 0.8 or 80%. It's a very, very simple rule, this rule of complements, but it's also probably the most important rule and useful rule of probabilities that we're going to be having in this class. And you're going to see it over and over again throughout the course. So I'll show you how to use that on another slide with an example other than this little easy example. Another rule we have is called the multiplication rule. So what it says is that if an experiment is run twice with replacement, then the probability of A and B is equal to the probability of A times the probability of B. As an example, let's suppose I pick 2 cards, but in a special way. I'm going to take a regular old 52 card deck that has 4 aces, by the way, and I'm going to pick a card, look at it, put it back in the deck, mix it a bit, and then pick another card and look at it. So I want to look at the probability of picking a card, seeing an ace, putting it back in the deck, picking another card, and seeing another ace. To find that probability, it helps to use this multiplication rule, because notice that this particular experiment is done with replacement, because we are putting it back in the deck after we've looked at the card. So we can say the probability of A1, I'm calling that A1 meaning the first card is an ace, and A2 meaning the second card is also an ace, is equal to 1 in 13, and that's reduced from 4 aces out of 52 cards. Or you could say there are 13 values and one of those is an ace. So 1 out of 13 for the probability of the first card being an ace. And then since we have replacement, the probability of the second card being an ace is also 1 out of 13. And what that is 1 over 169 when I do the multiplication. Notice this is very different than without replacement. So without replacement, this is not true. We actually get a different answer, and we'll talk about that next. So let me continue on. I want to talk about conditional probability. So to define that, I say the probability of an event A occurring, given the knowledge that B has already occurred, is denoted by the conditional probability statement. Probability of A, and we read this little vertical line segment with the word given. So this says probability of A given B. So an example, let's suppose I pick 2 cards, and now I am not going to replace the cards. I'm going to pick a card, I'm going to look at it. I'm going to take that card that I just looked at it, I'm going to put it aside. I'm not going to put it back in the deck. And then I'm going to pick a second card and I'm going to look at it. So the question is, what is the probability that the second card is a king, given that the first card is a king? So to find that probability out, it's no longer just 1 out of 13 or 4 out of 52, because we have information that the first card was a king. And because we know the first card was a king, we looked at that first card and we saw a king. There are only 3 kings left in the deck. There are also only 51 cards to choose from because we took that first king and we put it aside. That means there's only 51 cards left. So we could say the probability that the second card is a king, given the first card is a king, is equal to 3 divided by 51. If you want to reduce that as 1/17, you can, or decimal, I don't really care so much. So we have another multiplication rule that involves conditional probability. And that is that the probability of A and B is equal to the probability of A times the probability of B given A. Notice that this is different than the multiplication rule when we have events at which we had with replacement. Without replacement, you're forced to write it as probability of A times the probability of B given A. But if A and B are independent, and in the case of replacement, A and B are independent, but there's other cases also, then the probability of A and B is equal to the probability of A times the probability of B. So an example of 2 events being independent, let's suppose I flip a coin and then I roll a die. And let's suppose A is the event that the coin is a head, and B is the event that the die rolls on a 6. Then those are independent events because the probability of A and B, that is equal to 0.5 times 1/6, which is the probability of a head times the probability of rolling a 6. So notice that this equation does work. So the events A and B are independent. So there are actually 3 different equivalent definitions of independent. If you have one, you have the other 2. If you don't have one, you don't have the other 2. So the first one is the one I just said. The probability of A and B is equal to the probability of A times the probability of B. The second one is the probability of A given B equals the probability of A. So, for example, if I know I just flipped a head, that tells me nothing about what the roll of the die is going to be if I now roll a die. So the probability of A given B is equal to the probability of A here. If B is flipping a head and A is, say, rolling a 6, then the probability of rolling a 6 after knowing that you just tossed a head is the same as just the probability of rolling a 6, because tossing a head doesn't give you any information. This is symmetric, so we can also say that the probability of B given A is equal to the probability of B. So if we know that we had rolled a 6 when we rolled that die, then that gives us no information about whether the coin landed heads or tails. So that's why probability of B given A is equal to the probability of B. If any of these 3 are true, then all of them are true, and the events A and B are independent. So independence implies knowledge that one occurred does not change the probability that the other will occur. That's kind of the general way of stating it, but without doing the calculation, you can't be sure that they're independent. So here's an example. Let's suppose that out of 195 students who transferred from the community college last year, 112 took elementary statistics. 113 of the transferring students were women, and there were 78 women transferring students who took elementary statistics. That's a lot to talk about it. The question is, are the events women and took elementary statistics independent for transferring students? So let's talk about this one little piece at a time. We get to choose any of those 3 equations to check to see if they're true. But I'm going to first say the probability that somebody chosen at random took elementary statistics. Well, there were 112 people who took elementary statistics out of 195 total people, and people being transfer students. So that's 112 divided by 195, and I put that in my calculator. I got about 0.574. On the other hand, if we look at the probability that somebody took elementary statistics, given that the person is a woman, so now we're restricting our population to only women because we know that that person is a woman. Well, we know that there were 113 women who were these transfer students. So that's the denominator. That's the new sample space because I'm given the person as a woman. That changes the sample space to being a sample size of 113. Of those 113 women, 78 took elementary statistics. So the probability that somebody took statistics, given that they were a woman, is 78 divided by 113. And I put that in my calculator, and I got that that was about 0.690. Now notice that 0.574 is not equal to 0.690. In other words, we can say that the probability of A is not equal to the probability of A given B. So that taking statistics and being a woman are dependent events. Okay, they are not independent, so we say they are dependent. Okay, now let me talk about a very useful, not quite precise, but good enough for statistics, piece of information that talks about independent events. And that is the following. If the sample size is no more than 5% of the population size, then we can treat the solutions as independent events, even though they are slightly dependent. So this is especially useful in surveys taken from a large population, such as all Americans. And the idea, unlike the cards, when you're picking a card, and if you pick a king, and then you pick a second card, now there's a really big difference in the chance of getting another king. It went from 1 in 13 to 3 out of 51, or 1 out of 17. And 1/13 and 1/17 are actually pretty different. On the other hand, let's suppose we took a sample of, we asked 2 Americans at random. And the question is, are you a male or a female? Let's keep it easy. Well, if the first person that we asked was male, and then we do a without replacement study, which means the second person cannot be the same as the first person. Technically, we now have a different population because we're now not allowed to take that first person. But have things really changed in terms of gender distribution very much? If that first person we took out of the population and now we're going to ask a second person? Because maybe to 5 decimal places or so, maybe more than that, the probability of picking a woman, for example, hasn't changed to that many decimal places. So that's what this independence guideline uses. It says that in surveys, when we're talking about surveying all Americans or all trees in the Sierra Nevada mountains, if we look at a few trees, then even though we're not replacing the tree, we're making sure we're not duplicating, we can treat it as being independent. So that's going to be really important throughout the course. Okay, now let's talk about tables and probability. So here's an example. The table below shows the outcome of a recent survey on students' major. So let's see how you read this first. First, we got male and female. We got science, humanities, and other. So notice this 60, for example, means that there are 60 students who are male humanity majors. That's how you read this table. So let's use that to calculate some probabilities. So if a student is selected at random, find the probability that the student is, first, not a science major. Well, to find out the probability the student is not a science major, we can use a rule of complements. And we could say the probability that they're not a science major is 1 minus the probability that they are a science major. Well, how many science majors are there? There's 70 plus 50. That's how many science majors there are. And then how many total people are there? That's 70 plus 60 is 130, plus 30 is 160, plus 50 is 210, plus 80 is 290, plus 10 is 300. So notice there are 300 total students that were surveyed. So 70 plus 50 over 300, that's the probability that they are a science major. 1 minus that is the probability that they are not a science major. That's the rule of complements. And if you work that out, I got 180 over 300. Okay, now let's find the probability that this randomly selected student is male given the student is a science major. So if we're given the student is a science major, that means we're only looking at this area right here, science majors. We ignore all the other students. So we have a new population, and it's a population of science majors, and we want to find out amongst the population of science majors, what's the probability that the person is a male? So to do that, we just say, well, how many males are there amongst the science majors? There's 70. And how many science majors are there? That's 70 plus 50 is 120. And that's it. It's very easy if you know what to do, but it's also very easy to get confused. So when we have a problem that's asking for a given, so we're given information, that means we're restricting the population to just these science majors. Okay, now let's find out the probability that the student is a female and a humanities major. Okay, well, we don't need to use any special rules other than the definition of probability. So if we look at female and a humanities major, that's these 80 students right here. Those are the female humanity major students. And we're not restricting the population. They have to be a female and a humanities major out of everybody. So to answer the question, it's just 80. That's how many female humanities majors there are. Out of 300, that's how many students there are. Okay, now find the probability that the student is a male or a humanities major. Now I can use the addition rule. And that says the probability of being male or humanities major is the probability of being male plus the probability of being a humanities major minus the probability of being a male and a humanities major. So the probability of being a male, well, there are 70 and 60 is 130 and 30 more is 160 out of the 300 total students. The probability of being a humanities major, that's 60 plus 80 is 140 out of the 300 total students. And then there are 60 male humanity majors out of the 300 total students. 160 plus 140 minus 60 is 240. So the answer is 240 divided by 300. Okay, let me give you a little fundamental rule of counting, and it says the following. For a sequence of two events in which the first can occur in m ways and the second in n ways, the events together can occur in a total of m times n ways. This is very similar to the multiplication rule of probability, but now we're just counting the number of ways something can occur. So an example is if I pick a card from a 52 card deck and then roll a 6-sided die, then there are 52 times 6, and if I do that arithmetic, I got 312 different possible outcomes. And that's the multiplication principle. Okay? Often we call that the fundamental counting rule. And we're using that, and I'm not going to go into the big details of this, but if we're dealing with combinations, we're going to use the fundamental counting rule, but we're going to do that in a big way, which I'll show you how to do, and the calculator is going to handle it pretty nicely. So what it says is that the number of ways of selecting R items out of a total of N items to choose from, given that the order of the items is not taken into account, is, and the symbol is NCR. Sometimes you'll see an NCK there also, but I'm using NCR. We're going to be using a calculator, but just in case you're interested, is n factorial. Remember, that's n times n minus 1 times n minus 2 all the way down times 3 times 2 times 1 divided by n minus r factorial times r factorial. So this comes from the fundamental counting principle. I'm not going to go into the details here on why this is true and how it works, but you can just trust me that it does work. If you use a TI-83 or 84, or actually 89 also, and some other calculators, if we want to find the number of ways of selecting 5 items, for example, out of a total of 8 items, then we can type in 8, and then in the calculator, and I'll show you this in a minute, we go to Math, PRB, then NCR, then we type in a 5, and then hit Enter. And that will give us this 8 NCR5. So let's use it in kind of a fun way. I'm not sure if you've ever played the California lottery, but here's how the newest lottery works. At least the newest at the time at which I'm recording this. It changes from time to time. So to play the California lottery, you pick 5 numbers from 1 to 59 and 1 number from 1 to 35. And you win what they call the Powerball jackpot if your numbers are selected. So I don't know if you've ever played, but the question is, if you have played, you might be interested, what is the probability of winning the Powerball lottery with just 1 ticket? Right? If you buy a ticket, you think it's, very likely, should you just quit your day job and become a millionaire because that's what you're going to get? You're going to get, I don't know, $50 million, or sometimes it's almost $500 million. So the question is, what is the probability of winning? So notice, in order to answer this question, we can think of it as the numerator. The only way to win is for the California lottery officials to pick your numbers. And there's only one way for the California lottery officials to pick your numbers, and that's for them to pick those numbers. So the numerator is going to be a 1. The denominator is quite interesting. First, for these 5 numbers, from 1 to 59, the order in the lottery turns out not to matter. What matters is that they picked your numbers, not which order they picked them, for these 5 numbers. That's a whole different thing for the Powerball number. But for these 5 numbers, since the order doesn't matter and we're picking 5 numbers from 1 to 59, that number of ways of doing that is 59C5. But then you also have to get lucky, and they have to pick your Powerball number, the 1 to 35 number. There are 35 ways of doing that, of course, because it's 1 to 35. And since they're independent, what they picked from 1 to 59 for these 5 numbers is independent of the Powerball number, it turns out. So if you realize that, then we can use the multiplication principle and say the denominator, which is the total number of numbers that can be picked, will be 59C5 times 35. Let me show you in a calculator how to do that and how I arrived at 1 divided by 175,223,510. So again, you probably don't want to be quitting your day job on that because this is not very likely. And if you go to the lottery official rules on their website, you'll actually see this number. And now you hopefully understand how this came about. So let me show you how to use your calculator to come up with 1 over 59C5. I'm just going to do the denominator, 59C5 times 35. Okay, so here's the calculator. And I'm going to start out by opening a parenthesis. And then I'm going to go to 59, because we wanted 59, choose 5 is the way you say it. Then I'm going to hit Math. Then I'm going to hit the right arrow, 1, 2, 3 times till I get to PRB. And then I'm going to use the down arrow. 1, 2. I could also hit the number 3 if I want. Till I get to this NCR. And I'm going to hit enter. And then I'm going to pick 5, or I'm going to click on 5. End the parenthesis. And then we need to multiply that by 35 if you remember right, because those were the number of Powerball numbers. So times 35. And I hit enter. And lo and behold, I get 175,223,510, just like I expected. So the probability of winning the lottery, if you want to win the big, greedy Powerball super win, and you only buy one ticket, is 1 over 175,223,510. So that's all I have to say right now about probability. You definitely will want to practice. Watching it is not the same thing as doing it. And that's the hard part about probability, is knowing what to do when you are given a problem. So good luck on this. And if you have any questions, you can always email me and ask me about it, or email your instructor if you're from a different class. And hopefully this helped out. Thank you very much.